This is Daniel Coosbury, and this lecture is on the rational numbers. So the rational numbers get their name from this word up here that's in the name, the word ratio. And the ratio is simply can be written as one number divided by a number, or we can write ratios like using a colon. It expresses some sort of relationship between two numbers. So rational numbers is the set of all numbers that can be represented as a ratio or as one number divided by another number where those two numbers are integers. So, for example, like 5 over 7 is a rational number. Here's some examples down here. You have one integer divided by another. So here, and you could think of 7 as a rational number because 7 can be written as 7 divided by 1. You could think of 0 as a rational number because 0 could be written as 0 divided by 1. So there's a ton of rational numbers, and this is the really only restriction is you've got to have one integer divided by another in order to be considered a rational number. So this lecture, we're going to look at kind of how rational numbers work and how to play with them and convert them to decimals and do some arithmetic with them and a bunch of other things. Let's look down here. The fundamental principle of rational numbers says that if a and b is a over b is a rational number and c is any other number, that if we multiply the numerator and the denominator by the same number, this c, it's the exact same number, if we do that, we end up with the exact same number. So if we have a times c over b times c, this ends up being a over b, and we would call these equivalent fractions. Now, this may not make a whole lot of sense without looking at numbers, so let's look at some numbers. Here is a rational number, 308 divided by 418, and we want to write it in simplest form, which means we want to see if there's any way we can reduce this numerator and the denominator, and we're going to do that by finding some common factors. Now, in this case, I kind of been playing with these numbers, and you can kind of see they've got to have some factor in common, and I know ahead of time that the numerator is divisible by the number 22. So what I can do is I can write 308. I'll just go ahead and write the number. 418. So I can write 308 as 22 times 14. I just kind of break it up into those two factors. And I can do something similar with the denominator because it's also divisible by 22. That 418 is equal to 22 times 19. So what I've done is I've taken the numerator and the denominator and I've broken them up into factors. And I've done it in a way, and again, I've been kind of playing with this for a while, but I've done it in a way and I found that they each have a factor in common. It's a pretty large number. There's a 22. So based on this principle right here, if I have a number in common, I can pretty much just cross that out and write this rational number as those numbers that aren't in common, the ratio of these two. So in this case, I have a 22 in common here, and I can cancel those out, in which case my rational number is actually also equal to 14 divided by 19. So this big thing simplifies to 14 by 19. Those are what we call equivalent fractions. Equivalent. So we would call this simplest form because now we have 14 over 19, and neither of these two numbers have any more factors in common. They're not even. They're not both divisible by 2. So this is how we would complete this. Okay, we got a few different ways of representing fractions, and this is stuff you've probably seen at some point in your life. We have mixed numbers and we have improper fractions. Now the mixed numbers are the fractions that have two parts. They have a whole number part and then they have a fraction part. So typically we'll write the whole number a little bit larger and then the fraction part will be right next to it. So we'd read this as 2 5/7. And we want to convert this to an improper fraction. Improper fractions are fractions in which the numerator is larger than the denominator. So in this case, when we convert this, at the end of the day, the numerator should be much larger than 7, or a little bit larger than 7. All it's got to be is larger than 7 for it to be considered improper. So to do this, we'll use this method that's written up here. We're going to multiply the denominator of the rational number by the integer and add the numerator to this product. And then we're going to place the sum in step 1 over the denominator in the mixed number. So the way I like to do this is I've got a little visual that I keep in my head so I remember how to do this. That's not a 4, that's a 7. Is I'm going to take the whole number part and I'm going to multiply it by the denominator. That's the first step. So this is my little visual. Is I'm going to take the whole number, multiply it by the denominator, and that gives me 14. 2 times 7 gives me 14. And then I'm going to take the 14 and I'm going to add it to the numerator part. Okay, so I'm going to do the multiplication first, get 14, then add that to the numerator. So then my mixed number becomes 5 plus 14, which is 19, over the exact same denominator, which is 7. So when you do this conversion, the denominator never changes, but instead we have two whole pieces that turn into 14, two whole parts that turn into 14 pieces. Add those to the 5 pieces, you have 19 pieces now. This is your improper fraction. Okay, we can go the other way, starting with an improper fraction and convert that to a mixed number. To do this, you have to do division, and I prefer to do long division because we're going to have to do something with the remainder at some point. So you can do division in the calculator. The problem is the calculator is going to give you a decimal answer or something like that. But if you do long division, you get a remainder, which we can use to write this mixed number. So I'll show you what I mean here. Let's do long division. We'll do 47 divided by 8, and that's not going to be even, so we'll end up with a remainder. And 8 goes into 47 5 times. You do the multiplication, you get 40, a remainder of 7, and we're going to stop here. Okay, so now we've got some pieces here. We've got the remainders down here, the 7. We've got the original denominator. I'll just abbreviate that, denominator, this 8. And then we've got the quotient up here, this 5. So 8 goes into 47 5 times with a remainder of 7. So now using this part 2 up here, we can write the mixed number by writing the quotient, 5. This is the whole number part. The remainder, that should be, yep, the remainder as the numerator, and then the original denominator as the denominator. So again, in converting even both ways, the denominator doesn't change. We start out with an 8 in the denominator. We ended up with an 8 in the denominator. So this isn't too terrible either. Do the long division. You end up with 3 pieces, 1, 2, 3, and then just set it up in this way, which is kind of written up here, and that's how you do that. Okay. We can also express rational numbers as decimals, and to do this, you can pretty much do long division too. You just kind of want to end it in a different way. So for each one of these, I'm going to start doing long division as well. So I'll do 1 divided by 8 here. So 1 divided by 8. Except in this case, I don't want to leave a remainder. I want to end up with some sort of decimal. So what I'm going to do is I'm going to put a decimal right after the 1 where it belongs. We don't usually write it, but the decimal goes right there. And I'm going to add a 0 there because I can do that. You know, zeros at the end of decimals, we can write them or we can leave them out. So 1 is the same as 1.0. And then when I do that, I got to put a decimal up here. And then I can do some division. So I'm going to see 8 goes into 10 exactly 1 time. Then do the multiplication. I end up with 2 left over. And in this case, I want to keep going because I want this answer to look like a decimal. So this little blob thing should be a circle there, giant decimal. Okay, so then I'm going to add a 0 here because we can put as many zeros past the decimal as we want. This turns into a 20 then. 8 goes into 20 twice with a remainder of 4. And I'm going to keep going one more time. So I'll put another 0, bring it down. Then 8 goes into 40 exactly 5 times. Do the multiplication, you end up with 0 remainder. Okay, so since I now have 0 remainder, what I've done is I've expressed this fraction as a decimal. So 0.125 is my answer. So this is similar to what we just did with the mixed numbers, except in this case we don't want to just report the remainder. We want to put a decimal in there and we want to keep going so that we have a decimal answer. All right, let's do the same thing with this next number. So we want to write this as a decimal. We'll do the same kind of long division. So I'll do 5 divided by 11. And so that I get a decimal answer, I'm going to go ahead and put a decimal here, and put in my first 0 and start doing some division. So 11 goes into 50 4 times, and I get 44 and a remainder of 6. And as long as there's a remainder, I should keep going. So let me throw in another 0 and bring that 0 down. 11 goes into 60 5 times. I get 55, and my remainder here is 5. And I'm just going to keep doing this for a while, and I bring down another 0. 11 goes into 50 4 times. That gives me 44 with a remainder of 6. And then I'll put another 0 in there, and this is starting to feel a little bit familiar because now I'm seeing 11 goes into 60 5 times with a remainder of 5. And then if you notice, if I put in another 0 here, I'm going to end up dividing 50 by 11 again, and notice that I'm getting like some sort of repetition going on. So the numbers I got up here are 4, 5, 4, 5, and if I do this one more time, 11 goes into 54 times, I'm going to get another 4, and then another 5, and it's never going to end, which is not a problem for us because now we've noticed there's this pattern here that as long as we keep doing the long division, we're going to end up with the repeating decimal, 4, 5, 4, 5, 4, 5, 4, 5, so on. So this is not a bad thing. This actually means we're done because we've observed some sort of repeating decimal, and we have a way of writing repeating decimals that go on forever, especially since we can see this pattern. So we're going to write this fraction as 0.45, and we're going to put a little bar over the numbers that repeat. So in this case, we'll put a bar over 4 and 5 because that tells us that the number is 4, 5, 4, 5, 4, 5. It just repeats over and over again, and that means we're done with that. So hey, that's kind of nice. So the kind of takeaway for writing as decimals is you want to keep doing the long division until, in this first case, we finished and there's no more remainder. So see if there's no remainder here, so we're done. In this case, we end up with a repeating decimal, which once we observe that, so I see it coming up twice and it's still going to come up later, then that tells us we're done. So as long as the number is rational, we should end up with one of those two cases. All right, so let's work on going the other way now. So here are some decimals, and we want to write them as fractions. So we're going to call these terminating decimals in this case because they don't end up repeating like that last example. That is, there's no bars over this 0.3, so we don't read this as 0.33333, it's just 0.3. So to do this, I'm going to go ahead and take this 0.3. This is kind of how I like to think through this. This is 0.3. That's a 0. And I'm going to put this over 1 because I can do that with any number. 0.3 divided by 1 is 0.3. And I want to write this as a quotient of integers, which means that the numbers in the numerator and the denominator both need to be integers. So this can't be 0.3 because it's not an integer. We want to change that to an integer somehow. So in order to do that, I'm going to think, can I multiply this number by a ratio, some number divided by itself, so that that 0.3 becomes a whole number or an integer? And the answer is yes. I can actually take this and multiply it by 10 over 10. And if I do that, all that does is it takes, multiplying 0.3 times 10 takes this decimal, moves it over 1 decimal place to the right, and I end up with 3 in the numerator and 10 in the denominator. So that works. Let me draw that again. So that's all I really need to do there. Multiplying fractions is not a terribly hard thing to do. In fact, we'll do some more later. I can do the same thing here with 0.37. If I take 0.37 and I write it over 1, that's the exact same number. And I think, is there a number I can multiply by something divided by itself to make this an integer and not some decimal? And similar to this last example, yeah, the answer is yes. I can actually take this and multiply it by 100 over 100, which isn't going to change the number. It's just, and multiplying by 100 moves this decimal place 2 to the right, which is, so instead of giving me a decimal, it now gives me the number 37, which is an integer. And 1 times 100 gives me 100 in the denominator. So this is a way to write these numbers as decimals. I need to do this one. I'm just going to kind of do it down here. This third one is 0.024, which I'm going to work out the same way. I'm going to write it over 1 first, and then pick a number divided by itself that will make this 0.024 a whole number, or an integer. It could be positive or negative, so let's call it an integer. So if I multiply it by 1,000 over 1,000, then I end up moving the decimal in 0.024 3 places, 1, 2, 3, and that gives me 24 in the numerator and 1,000 in the denominator. Now that I've done that, I actually end up with a fraction that looks nice, but it's not exactly simplified because we can look at this and see, oh, both of these are even numbers and they have some factors in common that we should try to get rid of. So maybe we can write these numbers as something else and cancel out some things and simplify this. We didn't have that come up with these first two because 3 over 10 is in simplest form. Oh my goodness. And so is 37 over, I'm just not going to do that. So is 37 over 100. So I know that 2 goes into both of these. I think also 4 goes into both of these numbers. So I'm going to divide both these by 4. I'm going to break 24 up into 6 times 4. And I think I can break up 1,000 into 4 times 500. That is wrong. Let's do 4 times 250. So 1,000 equals 4 times 250. So since I have that common factor of 4, those cancel out, and I end up with 6 over 250. And that's still not in simplest form. So let's write this again. They both have a factor of 2 in them still. Let's write this as 2 times 3, and let's write this as 2 times 125. And I need some more space. The 2's cancel, and I end up with 3 divided by 125 as my final answer. So that one was a little bit more involved. Same process, got it as an integer over an integer, but I like to simplify things every chance I get. So this is that number in simplest form. We now have to deal with the case where we have decimals that aren't terminating. So here's that repeating decimal sign up here. That little bar means we're not dealing with 0.3. We're dealing with 0.33333 that goes on forever. And this is a little trickier to write as a rational number, but we can do it. So there's some steps up here that I'm going to follow pretty rigidly so that we get to that right answer. So I'm just going to kind of walk you through how this works. So the first thing is, this says let n equal the repeating decimal, which means I'm going to start by writing n is equal to 0.3333. So that's all step 1 means, is write that out. We're going to actually end up making an equation with n as the variable, so that's an important first step. Step 2 says multiply both sides of the equation by 10 if 1 digit repeats, by 100 if 2 digit repeats, and so on. In this case, we have 1 digit repeating, just 33333, which means we're going to multiply this whole equation by 10. So on the left side, this gives me 10n. On the right side, that would just move the decimal 1, and I'd still have a bunch of 3's repeating. So that actually gives me 3.33333. There's still a ton of 3's repeating. So when I multiply that by 10, I just get a 3 out here, and then the 0.3 repeating. Step 3 says subtract the equation in step 1, that's this first one, from the equation in step 2, which is the second one. So maybe I should rewrite that so this is kind of clear what we're doing. This is the equation we got from step 2, and we're going to subtract from it the equation we got from step 1. Oop, that should be a 3. Okay, so we're going to do some subtraction here. On the left side, I have 10n minus n, which gives me 9n. On the right side, I have 3.333333 minus just 0.333333. So if my decimals are lined up, these are actually going to cancel out, and I'm going to end up with just 3 on the right-hand side. So that was a kind of a weird step, but it's going to end up looking really nice. So I do some subtraction of equations here, and I end up with 9n equals 3, and then step 4 says divide both sides of the equation in step 3, which is this blue one down here, by the number in front of n, in this case 9, and solve for n. So I'm going to do some division, divide this by 9, just like I would any other equation. It cancels out on the left, and I have n equals 3 over 9, which reduces to 1 over 3. And that is my answer. So that was a weird process. You may have never done that before. But the good thing is these steps are pretty nice. They're in the textbook, and if you follow them to the T, then you should end up with something nice. So let's do another one of those just for good measure. Here's another repeating decimal. There's a lot more digits repeating this time. So this might be, I think this will be worth doing. So the first step says we're going to write n is equal to the repeating decimal. So I'm just writing that number up there. Second step says multiply it by 10 if there's 1 digit repeating, by 100 if there's 2, and by 1,000 if there's 3. In this case, I've got 3 digits repeating. So I'm going to multiply this equation by 1,000. And since I know I'm going to do some subtraction here in a minute, I'm going to write my step 2 equation up here just to save me some time. So if I multiply by 1,000, I get 1,000n on the left-hand side. And multiplying by 1,000 here would move the decimal 3 places. And then I'd still have some 257s repeating on the right side of the decimal. So this ends up with 257.257, 257, 257 over and over again. So I've still got this decimal repeating, but now I also have the number 257 before the decimal. So this is very similar to what we did on the last example. Okay, now I'm going to do that subtraction again, which gives me 1,000n minus 1n gives me 999n. On the right-hand side, I have 257 point and all that stuff, and then I have no whole numbers point the same stuff. This process ends up being the same thing as it did in the last example. This decimal cancels out with that decimal, and all I end up with is 257. So this method is designed to kind of make sure that happens every single time. So I have 999n is equal to 257, and I'll solve this. Step 4 says divide by this 999. This is just how we solve any one-step equation, is this cancels, and I end up with n is equal to 257 divided by 999. Wow. Let's try that again. 999. So that may be a weird process, but the steps work every single time for different sort of repeating decimals. And with that, you should have every tool you need to write fractions as decimals as fractions, and mixed numbers as improper fractions, and so on. So the first part of this section is simply getting used to how these numbers work and converting them. And the more you practice, the better you'll get at kind of figuring out what's the best thing to do and the best way to go with this. In the next lecture, we're going to look at multiplying, dividing, adding, subtracting, and doing some problems involving fractions. So that's what you have to look forward to.